Since this workshop is dedicated to Walter Craig, I just wanted to tell a quick story. So I actually met him at a Fields Institute workshop when I was still a graduate student. I learned a lot from him actually during that time. And he was a very captivating speaker. As you can see here, even when we're not discussing mathematics, still very captivating by this audience in the background. Some of you may recognize. So this was at another conference in Seattle a few years ago. We were on a way to a hike. It was a very eventful way, actually. On the way, we saw a brush fire. It was forest fire season. It was extremely hot weather. And our tire for the van that we were all in actually exploded. But I'm sure there's some joke about, how many mathematicians does it take to replace a flat tire. However, in practice, everyone was very efficient. We were in good hands. The real question really, and I think this is what the discussion here was about, was what was this fluid that leaked from the van as well. So I'm not sure that we ever came to a conclusion, but the long story short, we got a replacement van, so we were in safe hands again. We went on to our hike. So let's get to the talk. So I want to first of all thank the variety of collaborators that this work has been in. One of them is Paul Molesky, who was actually in the previous picture as well as Jean-Marc Vandenbroek, Emilian Parot. And more recently, some of the work includes my graduate students, Claudia Tugalon and Emilian Parot as well. And so here's a picture of them, because I bet they have their cameras off right now. So just in case, this is what they look like. But these days, because of COVID, this is actually more likely how you will find them. So in Canada, I guess face masks are still okay. It seems in the UK, they need a more elaborate solution of face shields and what appears to me a helmet. But anyway, so this is how you would see the collaborators more these days. All right, so the outline of my talk is I will briefly give the motivation for what I'm looking at, as well as how everything's formulated. And then I'll discuss both two-dimensional solutions of the model that we're looking at, as well as three-dimensional solutions. So in two-dimensional solutions, I'll also discuss some instabilities of what you'll see. And in 3 dimensions, for these flexural gravity waves, I'll talk about both forced and solitary waves. So the goal of the work, really, it doesn't matter if it's in 2D or 3D, is to efficiently compute solutions for different models for waves under ice. So I'll refer to these as flexural gravity waves. Once we do that, we'll compare their solutions. So the picture that I'd like to have for you to have in mind is, say you have a road over ice. So this is on the left is a couple of pictures of this road. So this is in northern Canada. And so say you have a truck traveling down this road. When people have looked at satellite imagery of what happens, they were able to see that actually as the truck travels, it displaces the ice cover, and the displacement look like waves. So, and these waves, or their displacements apparently are only sometimes even a few centimeters, but with these satellite imagery data, you can actually distinguish them quite clearly. All right, so the models that we're looking at is we're going to look at 3D as well as 2D waves propagating in their x direction. So we're going to have a sheet of ice on top, and then underneath you'll have water and a flat bottom. So I'm just showing these equations, even though I know that you're all familiar with them, but we're going to consider Euler equations, which describe an incompressible and viscid irrotational fluid. The velocity potential is phi, and the variable surface I'll often refer to as zeta, but I'm going to make a note, and sometimes I'll actually use zeta and eta interchangeably, but essentially they'll both describe the surface. So the zeta and eta actually depend on whether I'm talking in 2D and 3D. We've sort of used an inconsistent naming, but essentially the important thing is that the flexural part will come into the Bernoulli equation as this form dp flex, and d will be the flexural rigidity that will vary, and sometimes we'll have this pressure term if we're looking at, for example, forced waves, and this p will describe an external pressure exerted on the ice, and p flex will depend on the type of model that we're looking at. So the term for ice assumes that we have a thin elastic plate and the thickness of it is constant, at least for now. The ice bends with the water waves and there's no friction between the ice and the water. And we're going to look at continuous sheets, so there's no breaking. And so the flexural rigidity coefficient can be written in terms of the Young's modulus Poisson ratio, as well as the thickness of the ice. So here's little d that represents the thickness of the ice. So if you vary, for example, the flexural rigidity, you can think of it in terms of these parameters. And so the two different models we'll consider will be the biharmonic, and I'll often refer to it as the linear model, where you assume that the ice behaves like an Euler-Bernoulli thin elastic plate that gets deflected by a load, or Kosarat, which is a nonlinear model, assuming the sheet of ice can bend, twist, and stretch. And it also has an associated Wilmore energy as given by Plotnikov and Tolan. And you can describe it in terms of principal curvatures. And so there's a lot of work that has been done on this topic, and I'm sure I'm leaving out some people in this short description, and they might even be in the audience, so I apologize for that. So here are a select few. So since Greenhill in 1886, people have been deriving linear as well as nonlinear elasticity models, some that conserve energy, for example, Plotnikov and Toland or Kosarat model, and some models that do not conserve energy. And for review, you can look at Squire. People have looked at the existence of solutions, for example, in some parameter regimes, either using a Lagrangian formulation for traveling waves or a variational approach, and then showing existence, as well as looking at bifurcation theory for two-dimensional periodic waves. People have also looked at asymptotic models, such as looking at weakly nonlinear models like the NLS or the fifth order KDV. And so some people to name a few of these. And they've also looked at 3D asymptotic models as well, deriving a Benny-Roski-David-Severson type model. And then people have looked at solutions in 2D. So Vandenbroek and Parot, for example, looked at generalized solitary waves. And Gao and Vandenbroek looked at generalized solitary waves using a different model, the Plotnikov and Toland. And more recently, we've looked at the flexural gravity waves using a different method from the previous two. And people have looked at 3D solutions. So for example, Vandenbroek and Parot have been using the boundary integral method for looking at three-dimensional gravity, capillary gravity, as well as some models for flexural gravity waves. And more recently, Wang and Milewski showed that actually flexural gravity waves don't seem to bifurcate from zero amplitude when you're looking at the asymptotic models. And so that has a lot of implications for numerically when you're trying to do this. If the solitary waves do not bifurcate away from zero, then how do you get a good initial condition or initial guess for what your solution should look like that complicates your situation? And then also Tagoya and others, including groups with McHugh, have used high performance computing techniques to look at small amplitude solutions for wake patterns, looking for different kinds of wakes, using Krylov methods, preconditioners, parallelization, and even using GPUs to speed up their code. All right, so that's just an overview of some of the work. So what are we going to do? We're going to look at two different formulations. The first one is the boundary integral method based on the work by Forbes, as well as the Ablos-Fakas-Muslimani method. So if you've heard me talk, I've used AFM method before for gravity capillary waves. It's going to be similar for flexural gravity waves. And both of these methods have their advantages and their disadvantages. And really, they're the same disadvantages when you look at it, but the way that they show up is a little bit different. So you have small denominators in the integrands for the boundary integral method, and you have large, exponentially large terms in the integrands for AFM. And so the identity behind boundary integral method has small denominators because essentially you're looking at the fundamental solution to a Laplace equation that has these terms in the denominator that can get, so y and y star can get close to each other, as well as x and x star and z star. And so you might get terms that are close to zero, so you might have singularities in your integrand. And then identity behind the AFM method looks like this. And so it's a little bit less intuitive, but you can use divergence theorem and rewrite your Laplace equation in terms of non-local equation. And so the other thing we're going to do is we're also going to focus on the surface variables. I'm interested in what the surface of the wave looks like. And so we're going to rewrite everything in terms of the surface variables using the Zakharov formulation. So this changes our Bernoulli condition. And again, we have this term D times some sort of a model for the flexural term on the right-hand side. And that will depend on the type of model we use. All right, so that's briefly how we're going to reformulate things. So let's look at waves in 2D. So we're going to start with Euler equations, and we'll look at periodic solutions in this case. So we'll have this equation that's derived from Bernoulli that encompasses the flexural term. And then we're going to have this non-local equation as well that has hyperbolic sines and cosines. So for details, feel free to look at that paper. And so we're going to look at traveling waves. So we're going to go into traveling frame of reference, and we're going to look at the steady state problem. And so what we can do is we can reduce that two equations into one equation. So again, the flexural term is in here. There's the term D, which is the flexural rigidity, times this term that conserves the energy, which I'll show you more explicitly. For the linear model, looks like 4 derivative terms. So that's the bending of the elastic plate. The model is the ice, looks like this. And the nonlinear model is a lot longer because we're looking at how the curvature behaves. And so it has up to essentially 4 derivatives in eta. And so what we're going to do is we're going to look at bifurcation diagrams. So we're going to expand our wave surface in terms of cosine, or I guess really Fourier modes. But we'll find them symmetric so they can be represented by cosines, and we're going to generate a bifurcation diagram. And so, you know, further up the bifurcation diagram, we have higher amplitude waves. And so the one thing that we have to keep in mind, though, is that because we essentially have an interplay between the gravity term and a flexural term, we're going to run into resonances. And so John Wilkening had mentioned these in a talk yesterday when he talked about capillary gravity waves. You have Wilton ripples. In the case of flexural gravity waves, you can also have equivalent of Wilton ripples. And the way we'll parameterize these is if we fix the gravity coefficient, then what we can do is we can vary the flexural rigidity, and depending on how large this or how small the flexural rigidity term is, we're going to have different resonant modes that come into our solution. So what does that look like? So imagine we fix D to be this value, and we're looking at relatively shallow water. And I've not really shown you what the non-dimensionalization looks like, but here are parameters. And if we look at further and further along the bifurcation branch, the wave profile is bottom left. You can see that at some point resonances occur. And on the bottom right, we're looking at Fourier modes, and it's actually a semi-log plot. So if we didn't have a resonance, this plot would look like a line. But in this case, we have a resonant mode. K is 10, and so you can see this bump that comes in at 10, 20, and etc. So this is what the resonances look like. They very much look like the Wilton ripples that you get in capillary gravity waves, but that's the types of solutions you get. And the other interesting thing is that depending on the model, so if you're using the nonlinear model for ice or the linear model for ice, you can actually get to see different types of bifurcation branches. So in here, our D flexural rigidity is what I'll refer to as relatively small. The two bifurcation branches in red and blue lie on top of each other. And so there's very little difference between the model that you choose for the flexural term. But if you start to increase D, your bifurcation branch actually turns. So here it's going to the left. The wave profiles still look quite similar, but you're starting to see some deviation from what model you choose, from some dependence on what model you choose for the flexural term. And then if you increase D even more, so D is 0.3 in this case, you can see the bifurcation branches are starting to look even more different depending on the type of model that you choose to represent the flexural term. And at some point, you can even see that they actually will go, bifurcation branches will go in different directions. And so this is an even larger D. And so here's this, what the solutions look like. So the wave profiles, here I'm plotting both models, the linear, the nonlinear, more complicated model, where you're looking at curvature. So the wave profiles look quite similar, but the normalized wave speed actually, in this case, I want them to start off at the same point. The bifurcation branches actually, the direction of them depends on which model you're using to describe the flexural term. And so this is numerics, but we can look at asymptotics as well to see what's happening. So if we assume some small amplitude solutions, and we assume our velocity potential term is small, then we can look back at the time dependent equations and expand them up to order epsilon squared. Use this trick where we plug in capital Q to be the derivative of the velocity potential. And we're going to look at so we're going to look at solutions of the form eta 1 e to the I theta. So, we're going to look at multi-scale time. So we're going to also scale time. And we're going to group terms of different epsilon based on the harmonics. And what we can do is we can derive the NLS equation for the flexural gravity waves, which depends on, so here we've used the AFM formulation, we've derived the NLS equation for the different models for waves under ice. M depends on which model you're using. So here's the nonlinear model. M, it's going to look different from the linear model. And so what happens is now our stability of the solutions for flexural gravity waves will also depend on what model you're going to use to describe the waves. So depending on whether we have focusing or defocusing NLS, we're going to have different stability results as well. So here we go. So in here we have a plot that describes how the stability regime actually depends on the flexural strength and the model. So the blue line represents the NLS coefficient M. So that's the coefficient multiplying the nonlinearity. And blue is the linear model, the red is the nonlinear model. And you can see that for small flexural rigidity, the two models first go from unstable region to a stable region. And then when you're looking at higher and higher values of flexural rigidity, then the red model, the nonlinear model, stays for a long time. So it goes from being unstable to a little bit of stable and then back to unstable. So the nonlinear model will mostly be unstable for larger flexural rigidity terms, whereas the linear model will go towards a stable regime. And so this is what the asymptotic predicts. So let's look at the numerics. So let's perturb our traveling wave solutions with a perturbation of a different period. So this is what they'll look like. And the perturbation will depend on, the time dependence on it will look like lambda t. So we're going to set ourselves up for a spectral stability problem. And let's do the Fourier flow K decomposition, which has already been mentioned in the series of the talks that was part of the workshop. So I won't get into too much detail. When you substitute everything in, you can derive a generalized eigenvalue problem, which looks like this. And so what we're going to do is we're going to solve this generalized eigenvalue problem numerically. And we're going to look for when are eigenvalues growing exponentially. And so since this problem is Hamiltonian, effectively this reduces to us looking at when do we have eigenvalues that have some non-zero real part. And so we can also compare it to our asymptotics. So here's the NLS again, where the coefficients depend on the dispersion relation, and also the M encompasses the different models that we'll use for the flexural term. So we can perturb NLS as well with the time dependence given by capital omega of this form. And we're going to also have a flow K parameter too. So using asymptotics, we can actually look at when our maximum when the maximum instability occurs. You can actually see that it's M times amplitude. So here's the expression. And what we're going to do is we're going to look at the numerics and compare it with the asymptotics that we get. So the asymptotics will tell us when do we have a modulational instability, and the numerics can capture more than that, but we'll focus for now on the modulational instability. So here is comparison of instabilities for different wave profiles for linear, which is in blue, and nonlinear, which is in red model. So on the left-hand side are the 3 different wave profiles for the different models. They're right on top of each other, so you only see 3 different red lines. So we have a smaller amplitude wave, larger and larger. So there's 3 different wave amplitudes, and you can't really tell which come. So the red and the blue, linear, the nonlinear models are right on top of each other, so they give the same solutions. But when you look at their stability, in this regime, they mostly lie on top of each other. And so here you'll have dots, which represent the numerics. The lines represent asymptotics, but the dots and the lines are basically on top of each other. So in this regime, you can see that the asymptotics and numerics behave quite well for the modulational instability. And the only real discrepancy that you start to see is right around 0, where the nonlinear model gives you something that starts to deviate from these usual modulational Benjamin fear instabilities that have these figure eights. But everything sort of lies on top of each other, so there's good comparison. But when you look at a different value of D, and you start to compare the largest real part versus the flow K parameter, you start to see that actually the red model and the blue start to deviate a bit more. So the nonlinear model starts to show some differences between the usual Benjamin fear instability, which is that figure 8. When you look at the spectral plane, it looks even more. But essentially, the numerics and asymptotics are still relatively close to each other for the linear model for the flexural term. And so you can do all sorts of things by looking at the instability. So you can look at this, what we refer to as the high frequency instabilities. So away from 0 in the complex eigenvalue plane, you'll start to see all sorts of instability. So this is what the stability of this resonant profile looks like. And when you can zoom in, you can see all sorts of ellipses that you get in the spectral plane. And you can, they're all sort of lying on top of each other for the different models. But the important thing is there's still high frequency instabilities for these flexural gravity waves. So here we can do a growth rate, plot of the growth rates of the instabilities versus which parameter is unstable. And so you can see all sorts of variety of these instabilities come in, and they look quite similar to things that you may see in capillary gravity cases. But in this case, we're looking at flexural gravity waves. And so again, high frequency instabilities are also present, but they look quite similar between the different models, the linear and nonlinear. All right, so let's discuss 3-dimensional waves. So again, the 2 different models that we look at are the biharmonic or linear model. It looks a little bit different for the 3-dimensional waves. And the Kosterot model is even longer. So you have to look at the curvature again, so you have derivatives of your wave profile in X and Y and all sorts of combinations of them. And so the equations look like this. So again, you can put in different models into this term here. And you have kernels in your integram that could go to 0, but you can also take advantage of symmetries depending on the type of solutions that you're looking at. But you can also remove the singularity by using this formulation in Forbes, by noting that you can add and subtract a term, and that term that you're adding and subtracting, you can actually do the integral of it because it looks like a natural log. And all right, so we have the equation set up. Let's discretize. And here I just wanted to note that you're going to have, we use equally spaced points to discretize everything. And so you're going to have n points in X and m points in Y. And so our vector of unknowns is a lot longer, and we're looking at 3D. And so we're going to use finite differences to discretize the derivatives. And we're going to set up 2 times n times m equations. So the set of equations looks like this. It's a large set of equations, so it's computationally very intensive. And to solve the system, so I just wanted to put that in, we need to rely on a good initial guess. and we need a Jacobian matrix J. And so in this case, the Jacobian actually is quite complicated. So the sparsity of the linear Jacobian here is given in blue. So blue are all the non-zero terms of the Jacobian. And you can see that the bottom right corner is full of non-zero terms. And this is because you have a double integral over x and over y that comes from the boundary integral formulation. And then up here you have all the terms that look like this is from the flexural term. And so this method actually gets quite computationally intensive, or this formulation is computationally intensive, but there isn't necessarily a different way to do this, because even if you didn't have a boundary integral term, if you introduced, for example, if you went into Fourier space, then you might have your Bernoulli term, which gives you a dense part of the matrix. So the most computationally intensive part is computing the Jacobian. And you can consider two ways of solving the system of equation to avoid computing the Jacobian every time. So one way is to look at the inexact Newton method, which is direct, but you don't recompute the Jacobian every time you're iterating. Or you can look at the modified Newton method, which is an iterative method, and you use Krylov subspaces to generate Jacobian, and you focus more on the matrix vector product, so you don't have to store the whole Jacobian. And you can devise all sorts of different preconditioners for that. But I wanted to note that you can't get away with completely matrix-free methods, because the Jacobian is not sparse. You have some dense part of it. And the other thing that I wanted to mention is that there's lots of different regimes that you can look at these three-dimensional flexural gravity waves in. One way to look at the different regimes is, again, looking at the dispersion relation. So for example, if we look at the plot for when we take infinite depth, then you can compute there's a phase speed that has a minimum. So here's the plot. And so you can look to the left or to the right of the phase speed, and you will get different types of patterns. And so here are some different patterns. And what we're going to do for the purpose of this talk, so if you look at greater than u, if you have a disturbance that's moving at capital speed u, then these are an increasing speed of the disturbance. You can get different patterns that emerge, and we're gonna, for the purposes of this talk, focus on u less than c min, and we're gonna look at the different nonlinear models, nonlinear solutions, and the goal finally will be to consider solitary waves. And another thing that I mentioned is that not only does the method rely on a good Jacobian, but we also need a good initial condition. And so as I mentioned before, it's been noted that in some cases, it's not clear that solitary waves bifurcate away from a zero amplitude solution. So how do we get to computing these solitary waves? Well, we can first compute forced waves where we have some pressure term. And then we can, once we compute a branch of forced waves, we can turn off the forcing to look at the solitary waves. So in this case, we can, for example, look at the different pressures. So here's the form of the pressure. And so what we've done more recently, we've varied the shape of this pressure term, so making it, making the dependence in x, making it wider in x, or varying sort of the width of it in y as well. And the interesting thing is you actually get quite different patterns. So here's a cross section of these 3D waves as they depend on which pressure term you use. So the widest one is the dotted one. And so you can see actually the widest pressure does not give you the largest amplitude waves, but they do still give you the widest waves. And there's some sort of a maximum dip that you reach at, for example, Lx, the width of it to be 6. And so what we can do is now let's look at some cross section and compare the two. So here we have different forcing terms that we consider and how they depend on how the wave profile looks like. So here's the forcing that's a little bit skinnier in x, so Lx equals 2 versus Lx equals 6. So you can see that the red curve, so these are different cross sections in x for different values of y. So you could see that In here, systematically, the blue curve, so the larger pressure, it is larger in, it gives you a larger wave amplitude as well, but that's not always the case. So for Lx equals 6 versus Lx equals 12, it's a little bit different. So it doesn't necessarily mean that this wider pressure gives you a larger wave. It ends up actually being a smaller curve than in the red. And you can do this analysis looking at different pressures. And then the other thing that we've done is we've looked at what kinds of waves that you get from different linear and nonlinear elasticity models and how they compare. And so again, as we saw in 2D, actually, the wave profiles don't look too different from each other if you're looking at linear elasticity versus nonlinear elasticity. But what happens is that the models give the same similar looking wave profile, but for different Froude numbers. So just as they are giving us different bifurcation branches with respect to the wave speed, and here we've parameterized it a little bit differently and we're looking at Froude number, they give you different, both models give the same wave amplitude but for different Froude numbers. And then you can also look at the comparison of the wave profiles. And as you can see, the linear, the nonlinear elasticity models, they lie basically right on top of each other when you're looking at the cross sections of them. You can look for slightly larger amplitudes and they're still sort of indistinguishable almost. And then we can also look at bifurcation branches. So once we've generated a lot of the forced waves, so this is the dashed line. So we can look at elevation waves, which is the ones up here. And we can look at the depression waves, which are at the bottom below the 0 axis. So once we've generated enough forced waves, we can turn off the forcing and look at solitary waves. That gives you the solid line. So this is the bifurcation branches for infinite depth. You can look at the finite depth. It gives you a slightly different picture. And what do these waves actually look like? So let's focus on the solitary waves. So here are the branches overlaid with one another. So infinite depth, which is the dashed line, and the solid line is finite depth. And you can actually see that it's not clear whether the bifurcation branches for solitary waves actually go right to 0. And so what do these look like? So say we fixed some Froude number, and we're looking at solitary wave of depression in infinite depth. This is the profile in fully 3D. So this is computed on a quarter of a domain with n equals 80 points, m equals 50 points. And this is the spacing. We show this on the full domain. You can see that the cross section in X gives you quite a few more dips than in Y. In Y, it looks a bit more uniformly decay. And then here you can look at solitary waves of elevation in infinite depth with a Froude number of 0.53. And you can see in X, there's a lot more oscillations. In Y, you still have this more uniform decay. And then you can look at, for example, solitary waves of depression in finite depth in this case. And so again, this is computed on the quarter of a domain. And you can see that the cross section in Y again looks like uniformly decaying, but in X there's some oscillations. You can also look at solitary wave elevation. Again, fully 3D picture. So this is finite depth again, and you can see oscillations in when you're looking at cross sections in X. So you take a cross section, whereas you have uniform decay in Y when you look at the full domain. All right, so in this talk, what we've looked at is we looked at first waves in 2D, so periodic, as well as considering their stability. And so we saw that the high frequency instabilities are predicted by the linear dispersion relation, and it looked like they didn't really depend too much what model we used at, whether it was the linear elasticity model or the nonlinear elasticity model for flexural gravity waves. We also looked at the modulational instability and compared it to a derivation from an NLS approach and agreed quite well with the numerical methods. But the stability regions did depend on the type of model that we used for the flexural waves, whether we used the linear elasticity or the nonlinear model. And then we also we also showed that the Fourier-Floquet-Hill method could be easily implemented to find stability regions for very nonlinear solutions. And then in 3 dimensions, we focused on looking at forced waves as well as solitary waves. And we saw that in infinite depth, the branches reach higher amplitude and show more oscillations in X directions, but finite depth waves are less compact in the Y direction. It looked like the elevation waves were smaller than depression waves. And then it was not clear if we got agreement between the results from the asymptotics. Well, it was still hard to answer the question of do free surface depression or elevation waves bifurcate away from 0. Numerically, it's difficult to prove due to the computational cost and the resolution, but it sort of seemed that our numerics imply that perhaps they may not bifurcate away from 0. All right, thank you very much for your attention.